Okay, welcome back to the series of lectures on transform calculus. And in the last lecture we have introduced Laplace transform, and then we have evaluated Laplace transform of some elementary functions, and we ended up with the existence theorem, where we have seen that if a function is piecewise continuous and of exponential order, then the Laplace transform must exist. And in fact, these conditions are sufficient condition for the existence, and to support that we also discuss some examples. So, let me just recall briefly what we have done in the last lecture. So, the Laplace transform of a function f t, and we denote it by this f s. This will be given by 0 to infinity e power minus s t f t dt, and provided this improper integral converges for some s. And we have seen that if f is piecewise continuous function and of exponential order, then Laplace transform, that is LFT, exists for real s greater than alpha. And that after that we have made two remarks, very important remarks. One was that f s tends to 0 as s approaches to infinity. This is true for if the function f is piecewise continuous and of exponential order. So, for the Laplace transform of the piecewise continuous function and of exponential order goes to 0 as s approaches to infinity. So, here we can also conclude that if a function f s or a Laplace transform does not converge to 0, that means this is not the Laplace transform of a piecewise continuous and of exponential order function. And the second remark was to support that these conditions, that the function is piecewise continuous and of exponential order, they are sufficient condition. And then we have supported this argument with the two examples. The one was 1 over square root t, and this function is not a piecewise continuous function even though the Laplace transform exists. And the second was 2 t e t square cos or sine, also we can take e t square, and this function, because of this e t square, is not of exponential order, and the Laplace transform exists for this function. So, this was from the last lecture, and now we will continue this lecture with the properties of Laplace transform, and these properties will be helpful to calculate Laplace transform of complicated functions, and later on for the differential equations. So, we start with these properties. So, properties of Laplace transform, and the first property is the linearity. Linearity property, and it is easy to say that the Laplace transform of the sum of functions or linear combination of these functions f k's will be the sum of the linear combination, the sum of the Laplace transforms of these functions. And the proof is very simple. We can just take the definition, and we have the integral, and then the integral of this sum will be the sum of the integral, and from there we get directly this result. So, let us just go quickly with one example. So, the Laplace transform of cos omega t will be Laplace transform of e I omega t plus e minus I omega t divided by 2, and then the linearity property we use. So, we get half and the Laplace transform of I omega t and plus half Laplace transform of E minus I omega t, and these Laplace transform of these exponential function we have seen in the last lecture, and they are simply s minus I omega, this constant sitting with t, and plus we have 1 over s plus I omega. And if we simplify this, so we have in the denominator s square plus omega square, and then we sum these two. So, we will get 2 s and this 2 gets cancelled. So, we have s over s square plus omega square. And similarly, we can also get the Laplace transform of sin omega t, for example. So, this will be here the Laplace transform of e I omega t plus e power minus I omega t with minus sign. Now, we have sign and this will be 2 I. And now, again we use the Laplace transform of this and Laplace transform of this. So, minus will appear here and 2 I, and in that case we have these s will get cancelled and we have 2 I omega. So, 2 I will be cancelled again. So, here we will get simply omega over s square plus omega square. So, this is for the sine transform. So, this was the linearity property. Now, we move to first shifting property, where we can have shift in the time variable or in the s variable. So, there we have the first shifting property, and in this case it says that if Laplace transform of f t, as usual we denote by f s, then the Laplace transform E a t f t will be simply a shift in s. So, this f s will be f s minus a. The proof is simple. So, we start with this Laplace E a t f t, and then we have 0 to infinity e power minus s t E a t f t dt, and this is 0 to infinity e minus and s minus a. We combine these into 1 t and f t dt, and now as per definition we have just instead of this s here s minus a. So, this is f s minus a, because remember our f s is a Laplace of f t, that is 0 to infinity e power minus s t and f t dt. So, just here s is replaced by s minus a. So, we have this f s minus a. Now, go for the example. So, the Laplace transform of e minus t and sin square t. So, Laplace transform solution, the Laplace transform of sin square t first we need to get, and then we can apply the shift theorem to get Laplace transform e power minus t sin square t. So, here we can have this sin square t, we can write 1 minus cos 2 t over 2 and then apply linearity property. So, we have half and Laplace of 1 is 1 over s. We have minus half Laplace of cos 2 t, that is s over s square plus 4. So, this we get 2 over s and s square plus 4, because we will get there 4 and this 2 will cancel. To this 4 we will get 2 there and s over s square plus 4. So, this is our f s now, and now we get the Laplace transform of e minus t sin square t. So, this is by this shift theorem we have f s plus 1, because we have e power minus 1 here. So, we will get f s plus 1. So, that means 2 over s plus 1 s square plus 2 s plus 5, because we have here s. So, this s we can have s plus 1 here also s plus 1 whole square. So, we will get simply this term. Now, the next property, that is a second shifting property. Second shifting property. So, if the Laplace of this f t is f s and we have now shift in f. So, the f t minus a for t greater than a and we have 0 when t is between 0 and a. Then the Laplace transform of this g t function will be e power minus a s and f s. So, if we look at this g t, so if our function, this is f t for t, here the origin, and this is t axis and f t. So, this is our function f t, and if we look at the g t function, it is simply a shift. So, between 0 and a, our function will be 0, and then this t greater than a, it is just again f t. So, now we have this shift of this function, it's the same function, but with this shift g t, and in that case the Laplace transform is e power minus a s f s. So, we go quickly to the proof of this, and the Laplace transform of g t as usual is 0 to infinity e minus s t g t d t, and this is because this g t is 0 up to from 0 to a. So, we have a to infinity e minus s t, and this is in this range, it is f t minus a d t. So, what we can do, we can substitute this t minus a to a new variable. So, that we have d t is equal to d u, and now the Laplace transform of this g t will be the limits when t was a here. So, u is this 0 and infinity, it will remain infinity. So, e minus s and t is a plus u, and we have f u and dt is d u. So, e power minus s a is constant with respect to this u. So, we can take it out of this integral, and we have e minus s u f u du, and this is exactly the Laplace transform of f. So, here this is interesting, we have one alternative form which is normally used in the application, alternative form of this second shifting theorem. So, instead of defining that g with this f t minus a t greater than a and 0 between when t is between 0 and a, we can have a rather simpler form for this. So, if again the Laplace transform of f t is f s, then we can write simply the Laplace of f t minus a and multiplied by this h t minus a, it is a Heaviside function, I will define in a minute, and this is the same result what we have for the g t. So, minus a s and f s. Now, this where this h t minus a, or we can have t also. So, here we have 1 if t is greater than a, and this is 0 if t is less than a. Okay, so, what do we have here now? Basically, this is h t minus a, it is greater if t is greater than a, then this is 1. So, we have f t minus a for t greater than a, and when t is between 0 and a, this is 0. So, we have here the 0 function. So, this is exactly the function g t what we have in the earlier form. So, this g t, but just for the writing convenience, we can directly write this f t minus a h t minus a instead of defining that g t in that way. So, one example for this, find Laplace transform of g t where g t is 0 t minus 1 whole square and t greater than or equal to 1, and we have between 0 and 1 it's 0 and g t is t minus 1 square t greater than a. So, we can directly apply the shifting theorem now. So, first we need to get the Laplace of t square, and that is we know 2 over s cube, and then the Laplace of this g t, which is a shift here now, and we can directly by this formula we have e power minus a s, and a is 1 here. So, we have e power minus s and the Laplace transform of this t square, that is 2 over s cube. So, the next property, that is the change of scale property. Change of scale property. So, what this says, we have if the Laplace transform of f t is as f s, then the Laplace transform of f a t, so a is a constant, will be given by 1 over a and f s over a. So, for the proof we take this Laplace transform of a t, and by definition we have 0 to infinity e minus s t and this function f a t d t. Again we substitute this, a t is equal to u, and this is a d t is d u, and then our Laplace transform of f a t will be, the limits will remain 0 to infinity, and e minus s, the t is u over a, and this f a t is u, and we have d u over a. So, what we have here 1 over a and 0 to infinity, and e minus, instead of s we have s over a, u f u d u, and as per the definition now this is f s over a. So, we have proved the result that this Laplace of f a t is 1 over a, and this is f s over a. So, now we take the example that if the Laplace transform of f t is s square minus s plus 1 over 2 s plus 1 square and s minus 1, then find the Laplace transform f 2 t. So, Laplace transform f 2 t by this change of scale property, we have 1 over a. So, 1 over 2 and f s over a. So, we will replace this s by 2. So, s by 2 square minus s by 2 plus 1 over 2 and s over 2 plus 1 whole square, and s is s by 2 now minus 1. So, this we can simplify, and we will get 1 over 4 here, because you have the s square over 4 minus s over 2 plus 1 and there also. So, we simplify this to get s square minus 2 s plus 4, and same here we have this s plus 1 whole square and this s minus 2. Okay. Now, we go for the very important property of this Laplace transform, that is the Laplace transform of derivatives. So, this result will be very useful while solving the differential and partial differential equations. So, now we go for the Laplace transform of derivatives, or this is also known as derivative theorem. So, suppose f is continuous on 0 infinity and of exponential order, and that f prime is piecewise continuous on 0 infinity, then the Laplace transform of the derivative. So, df over dt is s, and the Laplace transform of f t minus f 0 for real s greater than alpha. So, here just one point I should mention, that if we have here this continuity in the open interval, then this will be replaced by f 0 plus. In that case, we will take only the limit of f, the right limit, instead of the value, but if f is continuous at 0, then this is just f 0. So, the proof of this, so we have Laplace transform of f prime t, and we have 0 to infinity f prime t e minus s t dt, and now we integrate this by parts. So, we have this integral of this is f t and e minus s t. So, here the limit 0 to infinity minus 0 infinity, we have again f t and e minus s t and minus s dt. So, here as t approaches to infinity, this will go to 0, that we have seen in the last lecture, because this function is of exponential order. So, this will go to 0, and then as t approaches to 0, we have f 0. So, we have here minus f 0 and minus minus plus here s, and then 0 to infinity f t e minus s t dt, and this is the Laplace transform of f t. Okay, and this is for real s greater than alpha, because for that only this will be 0. So, this is the result now, f t minus f 0 plus s Laplace transform of f t. So, here the interesting feature is that without having the condition that the f prime is of exponential order, here we assume that f prime is only piecewise continuous, and what we get here, that the Laplace transform of f prime t will be just minus f 0 plus s Laplace transform of f t. So, without requiring that this f prime itself is of exponential order, we can get the Laplace transform. And in fact, if we remember that today itself we have seen that this function 2 t e t square and cos e t square, the Laplace transform of this function exists, and this is not of exponential order. And now the reason is very clear, because this function is the derivative of sin e t square. So, it is a cos, and then the derivative of this will be 2 t e t square. So, this is the derivative of this function, which is here continuous, and it is of exponential order, but its derivative is not of exponential order. But now we do not need basically this condition on this derivative, and we can get the Laplace of this derivative. Okay. So, one more remark. we have here that this result we can also generalize this. So, the above result can be generalized. So, for higher order. So, now for the Laplace transform, if we want to take for the double derivative, then we have the Laplace transform minus the f prime at 0 as per this the Laplace transform of the first derivative, we have minus f 0 and s Laplace transform of f t. So, plus this s and the Laplace transform of f prime t, and now again we apply here. So, we have minus f prime 0, we have s minus f 0 plus s Laplace transform of f t, f t, the Laplace transform of f t. So, what we got here, s square Laplace transform of f t minus this s f 0 and minus f prime 0. This is the Laplace transform of f double prime, or in general we have the Laplace transform of f, the nth derivative s n, the Laplace transform of f t, and minus s n minus 1 f 0 minus s n minus 2 f prime 0 and so on, minus f the n minus 1 at derivative at 0. So, this is the general form of this derivative theorem. Now, we quickly go for one example. Determine the Laplace transform of sine square omega t. So, here we can use this derivative theorem, because we know that the if f t is sine square omega t, then f prime t is simply 2 sine omega t, and then sine omega t derivative will be cos omega t, and we have omega. So, we have omega and 2 sine omega t cos omega t is sine 2 omega t, and the Laplace of this we know. So, the Laplace of omega sine 2 omega t, which is the derivative now, and we apply the derivative theorem. So, the Laplace of the function, that is sine square omega t, and minus the function value at 0, and this is 0. So, this we know omega is a constant, and 2 omega t sine 2 omega t will be 2 omega, and we have s square plus this 4 omega square for this, and we have one s there, 1 over s, and so this is the Laplace transform of sine square omega t. Okay. So, now the next property of this Laplace transform, and that is the, if we multiply the function by t power n, then what will be the Laplace transform. So, multiplication by t power n. So, if the Laplace transform of f t is f s, then the Laplace transform of t f t, we have multiplied by this t, will be simply minus d over d s and f s, and in general also this result is hold. That means the Laplace of t n f t will be minus 1 over n, or minus 1 power n, and d n over d s n, and the Laplace transform of f t. So, this is the general result. So, proof first for this particular case when this n is 1. So, what is given, that this f s, that is the Laplace transform of f t, as 0 to infinity e minus s t, and f t dt. So, we will prove this, we will start with this side and we arrive that this d over ds of f s is nothing but the Laplace transform of t f t. So, here now we have f s, now we take the derivative with respect to s. So, d f s over d s will be 0 to infinity. So, with respect to s, so we apply the Leibniz rule for differentiation under integral sign, and we assume that we can do apply here. So, 0 to infinity and this derivative with respect to s, from here we have e minus s t, and the derivative of this minus s t with respect to x, so s we will get minus t, and then we have here f t and this d t. So, now what we get here minus 0 infinity and e minus t, and we have t f t. So, instead of this f t we got the new function t f t, and this is the Laplace transform of t f t. So, minus the Laplace transform of t f t and the repeated differentiation. So, we take once more this differentiation with respect to s, and we will get for the second derivative. So, given or differentiation gives the general rule. So, we do not have to prove this general rule, this is one can simply go with this higher derivatives here and can get it. So, let us go for the example. So, Laplace transform of t square cos a t solution. So, we have Laplace of this cos a t we know, and that is s over s square plus a square. So, we can have now the Laplace for t square cos a t, and the rule says minus 1 power n. So, n is 2 here, and d 2 over d s square, and the Laplace of this function, that is in our case cos a t. So, the Laplace is s square plus a square. So, this is 1, and we have d over d s, and here we differentiate this. So, s square plus a square whole square, s square plus a square, and derivative of this is 1 minus s as it is, and the differentiation of this we get 2 s. So, we have s square minus 2 s square will get minus s square. So, a square minus s square plus a square, and this whole square. So, we differentiate this again and we get finally the 2 s square minus 3 a square over s square plus a square 3. Okay, so, the next property we have the division by t. Instead of this multiplication, now we have division by t. So, if f is piecewise continuous on 0 infinity and of exponential order. So, piecewise continuous and of exponential order alpha, such that the limit t approaches to 0 plus f t over t exists, then we have the Laplace transform of f t over t s to infinity and f u du for s greater than alpha, if we just take the real s. So, for proof we let this g t, this function here f t over t, so that we have f t is t gt, and then we take the Laplace of f t, or that is f s. This Laplace of f t is t g t, and we apply this result what we got as a last property with t g t. So, we have minus d over d s, the derivative of the Laplace transform of g t, and this is what we want to get. So, now what we do, we integrate this with respect to s, integrating with respect to s from s to from 0 to infinity, from 0 to infinity. So, we integrate here, this is the Laplace transform of g t we will get, and this limits from 0 to infinity. So, we will get minus Laplace transform of g t, and our limits from 0 to infinity, and the right side we have. So, this side goes to this, we have s to infinity. Sorry, we need to integrate from s to infinity. So, integrating with respect to s from s to infinity, from s to infinity. So, s to infinity, and minus we have again s to infinity and f s d s or f u d u. Now, what this gives us when we take this t approaches to this s approaches to infinity, this is the function of s only, Laplace transform of g t. So, as s approaches to infinity, this will approach to 0, because this g t is just f t over t, and this limit t tending to 0 exists. So, this is a function then of exponential order and piecewise continuous, because f t is piecewise continuous and t is also piecewise continuous, and this limit which was the singular point basically, but we assume that this limit exists. So, once this limit exists, this function f t over g t is piecewise continuous and of course, of exponential order then. So, in this case the result says that the Laplace transform of any piecewise continuous and exponential order function will vanish as s tends to infinity. So, this will be 0 and then minus plus, and then we have this s. So, simply the Laplace transform of g t, and this is s to infinity f s d s. So, this is the required result. So, we just go for one example. So, find Laplace transform of sin a t over t, and Laplace of sin a t we know it is a over s square plus a square. Then with this property we can get sin a t over t s to infinity a over s square plus a square ds, and this is tan inverse s over a, and the limit s to infinity. So, when we put s to infinity, this will be pi by 2 and minus tan inverse s over a. So, now the next property is the Laplace transform of integrals. Laplace transform of integrals. So, suppose f t is piecewise continuous on 0 infinity, and the function g t 0 to t fu du is of exponential order, then the Laplace of g t will be 1 over s f s. So, we look at the proof. So, what we see first, that g 0 is 0 because the t will be 0. So, we have this integral 0 and the derivative of this g is f t. So, derivative is f t, and then we use derivative theorem that the Laplace of g prime t will be the s Laplace of g t minus g 0. And note that we can apply this derivative theorem because g t is piecewise continuous. In fact, it is a continuous function, one can show, because f t is piecewise continuous and we have the integral here. So, g t is of course piecewise continuous and is of exponential order. So, g t is a piecewise continuous and of exponential order, and this g prime t, which is f t, that we have assumed that this is piecewise continuous function. So, the derivative we need only the condition that it should be piecewise continuous and the function should be piecewise continuous and of exponential order. So, we can apply this Laplace this derivative theorem without being this g prime to be of exponential order. So, this is okay to do that. Here Laplace of g prime t, we have this result, and in that case we directly get this g 0 is 0. So, this term is 0 and the Laplace transform of g t then is 1 over s and the Laplace transform of f t. So, now the example that the Laplace transform of 0 t sin u over u du. So, this Laplace transform by this property, we have 1 over s and Laplace transform of the function which is sin t over t. So, we have 1 over s and then divide by t, that property we can apply. So, s to infinity and the Laplace of sin t and ds. So, we have 1 over s infinity Laplace of sin t 1 over 1 plus s square ds. So, here we have tan inverse s. So, pi by 2 minus tan inverse s, and this is 1 over s, and we can also write this cot inverse s. So, the next property is for the periodic function. So, Laplace transform of a periodic function. So, if a function is periodic, we can get this Laplace transform with a formula which is much simpler than going directly by the definition. So, if f be periodic function with period t, so that we will be talking about more on this periodic function in Fourier series. So, here let me just go through quickly. So, we have the periodic function of period t, and it must have then that f t is equal to f t plus this period t. So, in that case, if we have this property of the function, then the Laplace transform of this f t will be 1 over 1 minus e minus s t, and the integral 0 to t, capital T minus S t and this f t dt. So, here the proof, we have the Laplace of this f t, which is 0 to infinity e minus S t and f t dt. So, we break this into two parts. So, 0 to t, capital T e minus S t and f t dt, and the rest, that means t to infinity e minus S t and f t dt. And now, in this part, if we substitute that a new variable of integration tau is equal to t minus the period t, in that case we have what we get now. So, d tau will be dt. So, what we get 0 to t e minus S t and f t dt will be this tau. So, the t was tau, then t was this capital T. So, the tau is 0, and for the infinity we get again infinity e minus S, and this t we can replace by this tau plus t, and this f, the t is tau plus t, and then we have this d tau. And since this f is periodic function, so this is f tau again. So, tau plus t is f tau. So, e power minus S t, so here is the plus sign. So, what we get now, so this e power S tau, we can S t, e power minus S t, we can take out of the integral, and the remaining integral 0 to infinity e power minus S tau f tau d tau is the Laplace transform of f t again. So, that we take to the left hand side and then take this common, the Laplace of f t and the Laplace of f t here, then we will get 1 minus e power minus S t, and that we can divide. So, what we get now, the Laplace transform of f t is 1 over 1 minus e minus S t and 0 to t e minus S t and f t dt. So, this is the result, and if we just take one example to show this, that find the Laplace transform for the function f t, which is defined as 1 and 0 when t is between 0 and 1, and if t is between 1 and 2, it is 0, and then this periodicity we have that f t plus 2 is f t for all t positive. So, what we have, this function between 0 to 1, it is 1. So, 0 to 1, and then 1 to 2, it is 0, and then we have this periodicity. Okay, so, if we just go for the Laplace transform of f t, which is 1 over by this formula 1 minus e minus this t, our period is 2. So, we have 2 s, and we have 0 to 2, and e power minus S t f t dt, and this is 1 over 1 minus e minus 2 s, and 0 to 1, because from 1 to 2 this f t is 0. So, we have e minus S t and dt, which we can integrate. So, 1 over 1 minus 2 s, and we get minus s and e power minus S t. So, when t is 1, so we have e power minus s minus 1, and this we can simplify again. So, we will get s and 1 plus e minus s. So, now there are at the end we have two limiting theorems, and that is they are also useful. So, we have the limiting theorems. So, the first theorem is the initial value theorem. So, this initial value theorem says that suppose that f is continuous on 0 infinity and of exponential order alpha, and f prime is also piecewise continuous on 0 infinity and of exponential order, and then if we let this f s, the Laplace transform of f t, then f 0 plus. So, the right limit of f at 0, or this is just t approaches to 0 from the right side, f t, and this is just the limit s to infinity s f s, and this is for s real. So, the proof we can very quickly we can go. So, f prime t is the Laplace of f t and minus f 0 plus. This is by the derivative theorem. And now, if we take let the s approaches to infinity, and we have assumed that this f prime is piecewise continuous and of exponential order. So, this will go to 0. So, we have the limit s approaches to infinity s f s minus f 0 plus, and this is the required result. So, at the very end we have this final value theorem. So, suppose that f is continuous on 0 infinity and of exponential order alpha, and f prime is piecewise continuous on 0 infinity, and furthermore the limit t approaches to infinity f t exists, then the limit t approaches to infinity f t. So, in this case we are getting this limit as t approaches to 0 instead of t approaches to, or t approaches to infinity instead of t approaches to 0 in the earlier case initial value theorem. So, but this we can get by limit s approaches to 0 s f s, and f s is the Laplace transform of f t. So, here the point is that this is very important. The limit t approaches to infinity should exist, because if just for example, if we take the case that the f t is sin t, and then we get this limit s f s as s approaches to 0, and this we can get. So, limit s to 0 and s f s is s over 1 over s square, and this is 0. So, this limit we got here 0, but this does not mean that the t approaches to 0 the sin t is 0, because this limit does not exist. So, this is equal when this limit exists. So, this is very important to have this, and with this we can just very quickly just see one example, that without determining this f t and assuming that the f t satisfy the hypothesis of the limiting theorem, we want to get this f t and this limit t approaches to infinity f t if the Laplace transform of f t is given, that is 1 over s plus tan inverse a over s. So, we can get this, the t approaches to 0 f t by the initial value theorem, and this is equal to s approaches to infinity s f s. So, limit s approaches to infinity s f s, we have 1 plus s tan inverse A over S, and as s approaches to infinity. So, this is 1 plus this limit, which is infinity, and then we have tan inverse 0. So, we have 0. So, to get this 0 over 0 form, we take tan inverse A over S divided by 1 over S, and then we apply the L'Hopital rule. So, in that case this limit would be 1 over the derivative of this 1 over A square over S square and its derivative minus A over S square, and the whole will be divided by minus 1 over S square, the derivative of 1 over S. And now, if we let this S approaches to infinity, so this S square gets cancelled, and we have simply here A over 1. So, it is A. So, we get 1 plus A its limit. Now, if we take the another one for the final value theorem, that t approaches to infinity and f t is limit s to 0 and s f s. Now, if s to 0, so this is again the limit s to 0 1 plus s tan inverse A over S, and this s to 0, this is pi by 2. So, we have just 1. So, with the help of this Laplace transform, we can get two limiting values of the function as t approaches to 0 and t approaches to infinity with this limiting value theorems. Okay, so, we end this lecture here, and we have discussed now various properties of the Laplace transform, and with the help of these properties, in the next lecture we will continue to get to evaluate the Laplace transform of some complicated functions, and then those functions will be used for the application part where we will be solving the differential equation. So, that is all for this lecture. Thank you. Goodbye.